Okay, let's go. We have more stuff. Right, like 9 more. Yep, 9 more to go. So let's do that then. What will the rules be? The timer should be on. The rules are going to be that quad means that all 2x2 regions have to have at least one mine in them. Eyesight means numbers see how many non-mines there are in the 4 directions. Cool, okay. So we know that this 8 and this 5, I'm gonna use a darker color this time, blue should work. This 8 and this 5, or this 8 can only see a maximum of 5 in the horizontal direction, which means it must see at least 3 more in the vertical direction. These two are empty. 9. Well, again, this 8 can only see a maximum of 5 in the horizontal direction, and therefore I must see at least 3 more in the vertical direction, so that has to be empty. Now this 9 always sees 1 more than the 8 horizontally, right? Because they see the same number of cells vertically, so whatever the 8 sees, the 9 must see 1 more, so these are all empty as well. This time the 9 can only see 5 horizontally, right? Therefore, it must see at least 4 vertically. At least 4 more vertically. So this has to be empty as well. This 5 is... Well, okay. I think this 5 and this 7 work together. Oh, we can first put a mine here definitely because of quad. And here as well, there can be a mine there. It doesn't help us explicitly, but okay. I mean, we know that this 5 is either a 4 or a 5 vertically. If it were a 4 vertically, then this 8 would be a 6, no, a 5 horizontally, and this 9 would be a 6 horizontally. Yeah. I think that this has to be a mine. Right? But the other choice is if this 5 saw 5 vertically, and this would see 3 horizontally, this would, not 3, this would see 4 horizontally, this would see 5 horizontally. Oh, the blue is just not possible because of this 5, I just realized. Yeah, the blue is not possible, so the purple has to be true then. So there is exactly 5 vertically here. And then because there's 4 horizontally and 5 horizontally here, we can say that this 5 can't see this, otherwise it would see 2 more vertically, and then that would be a 6, so that can't be a mine. This 7 sees 5 horizontally, so it needs to see 2 more vertically. Now 5. Well, at most, the 5 can't really see this. Oh, but we do know by quad this has to be a mine. And in fact, because of this 5, this has to be a mine as well. This 5 sees 4 horizontally, so it needs to see 1 more. And this 4, well, this must be a mine because of quad, yeah. So this 4 sees 2 vertically, so you see 2 more horizontally. This 5, well, we know that's a mine, so this 5 sees 2 more, like that. This 5 over here can be complete. This 5 means there is a mine here, because of quad as well, so that's empty. This 5, well, can be completed like that. Because of quad, that's a mine, and because of the 3, that also happens. I don't think this 5 is resolvable, although we do know this is a mine because of quad. Okay, I think we look at this 5 and this 3 now, because the 5 cannot connect to this 3, otherwise it would be a 4. Yeah, otherwise this 3 would be a 4, and this 5 can only see 2 more, which means that at the very least this has to be a mine, and then this has to be empty, so that's empty. 4 here. Well, we know that there can only be a maximum of 3 here because of the 5. In fact, there must be exactly 3 here because of the 5. So the 4 can only see 1 more vertically. That's a mine. We also do know from this 3, because it cannot extend all the way out here, that at the very least this has to be a mine, and then this would be empty. And this 3 now, oh, okay, we look at something a bit more interesting here. We know that the 3s see the same number vertically, so they must see the same number horizontally. What that means is that if they both saw 1 horizontally, then you would break the quad. So they can't see both 1 horizontally, and therefore these are both mines, and the 3s must see this. The 5 can see 2 more before a mine, and this 4 can see 1 more before a mine. This 5 now needs this to be empty, so this can be a mine. And because of quad, this must be a mine, therefore this 4 makes this empty. 3 here means that, and then this 3 here means this is always empty. No? Oh, it sees 3 horizontally. What am I doing? I am tripping. Alright, well, there goes a lot of my time. Yeah, that should have been done like a long time ago. Jeez. Okay, well then. Okay, the final step. After all this, we know there's 1 mine remaining, and then there is a quad here that must have at least 1 mine in it, so that's where the mine has to go. These are all empty as a result. The 3 must therefore see no mines here and here. This 4 must see no mine here, so that's a mine. Nice. That was cool. Oh, crap, timer, right. 6 minutes. Was not that slow. Alright. Let's do another one. Connected and multiple. So connected means all your mines must be together, no isolated. And multiple means shaded mines count as... Oh, you can't really see the mines, huh? Alright, hold on. I'm gonna go ahead and change the mine color to a nicer color. I don't know if like this is a nicer color. I can't really even tell the difference between maroon and like black, but sure. Does that help? Yeah, it does. The mines in shaded cells count as 2 mines instead. So let's begin with this 2 probably. If there were a mine here, then this is not a mine, and this is not a mine. That isolates it, so it acts a bit like a 1 in connected. 0 means no mine here or here, therefore that's a mine and that's not. 8. Wow, this 3 must have mines here and here. Well, this 8, I'm pretty sure all 3 of these must be mines. Right? Yeah. And then 1 of these are mines. But because this 3 sees a 2 already, it cannot see another 2. 5 and 2. This 2, okay. Let's think about, I'm pretty sure that mines, okay, the mines either go out here or here. Because they cannot go out through here, right? Yeah. Number 1, we know that there has to be some number of mines here. Because of the 5, there's only 4 here maximum. So we know there has to be some number of mines here. For these mines to exit, if they attempted to exit this way, then the 2 would fail because, you know, you have to have a mine here, and then 1 of these has to be a mine, which fails because your 2, well, you could have a mine here. Oh, but then 1 of these would have to be mines, which then fails your 2. Okay. So, again, it cannot do this. Therefore, it must come out through here or through here. However, if it came out through here, you'd have a mine here, and that instead breaks the 3. So that means that I think these are both mines. Nice, alright, and this 2 is just completed. This 2 means this is a mine and this is not. This 5 sees 2 so far, so it sees 3 more, which means this is always a mine. And therefore 1 of these is a mine, which would complete the 3. So that's not a mine and that is. The 4 sees 4, so that's not a mine, so that is a mine. This 3 is complete. And this 2 can be completed. This 4 sees 1 so far. I need to see another 1 to make an even number of mines. And this 3, well, can only be done with a 1 and a 2. finishing this 4. This 4 is also complete, so we can do that. This 7 sees 5 so far, so it needs 2 more, which can be done like that only. This 8 sees 2, 4, 6 so far, so it needs 2 more again, like that. 9, we're just gonna keep getting bigger numbers. 3 means that this has to be a mine and this is not. We know this has to exit out here somehow, but I think the 7 guarantees that as well. The 7 sees 2 so far, so you see 5 more. Pretty sure, yeah, none of these can be empty. If any of these were empty, your remaining cells will only add up to 4. So it'll be both mines, and then one of these are mines. The 3 over here sees 1 already, so it needs to see a 2 more, meaning this is not a mine. And therefore this is. This 7 sees 5, so you need to see 2 more. That's a mine that isn't. This 3 is complete. This 5 is also complete. This 4 can be completed like that. And we use this 9, sees 2 so far, so you see 7 more. With 4 mines remaining. Okay, everything's connected so far, so we can't use connected logic right now. However, because we need 7 more, if this was empty... Oh wait, is it just complete? No. If this was empty... Oh, you need 5 more, not 7 more. Yeah, 5 more, not 7 more. Alright, well... 5 more can be done in a few ways. But... assuming this was empty, you then have 4 mines here to make up your 9. That would finish the mine count, but I think this is fine because everything is connected, I think. Yeah, everything seems to be connected. Is there any way to make it more... Yes, there is one way to put a mine here and a mine here. Ah, then you use a 3rd mine, correct? And this is as low as you can go. 3 mines. A 9 plus like 1 of these being mines. So, at the very least, this set of 5 must have 3 mines in it, at the very least. Meaning this cannot be a mine. Because if it was, none of these would be mines, which isolates it. So, that can't be a mine. 0, alright. So now we do know there are 4 mines here. Which means that it is... well, this 3 sees 1, so you see 2 more. We do know if it saw 2 like this, then you wouldn't have enough space to put 4 mines in it. So it can't be like this, and therefore must have its 2 mines be single. This 3 is then complete, allowing us to finish 9. Nice. That was cool. The rest of my timer is... Shit, is it off? No, it's not. The colors are exactly right. Alright, next puzzle. Liar and triplet. I thought I've done this before. Basically what liar is... See, I apparently have not done liar triplet. But what liar is every number is 1 more or 1 less than its actual value. Triplets means that mines cannot form a row of 3 orthogonally or diagonally. So you can't make 3 in a row basically. So we start this 5, which cannot be a 6 because it doesn't have 6 cells around it. Therefore must be a 4. We'll mark it with a lower symbol here. And a 4 on the side in triplet is very useful because that implies that these are both mines and these are both non-mines. You can try to figure out the logic yourself, but yes. The 4 here can't see 3 in a row this way, so this must always be a mine. And since... oh no, this 4 is a 3. Yeah, the 4 is a 3. I almost forgot. And because it's a 3, we know there's 2 mines here. This 2, well, we know this 2 is probably a 3 then, because it can't be a 1 anymore. Not sure if I can do anything about that though. This 3 is probably a 2 as well, because it can't be a 4. Otherwise, all of these are mines, which breaks. So this 3 is a 2. Yeah. Oh wait a minute, this 2 is I think complete, yeah. Yes, because we know that this 5 has exactly 1 here. And this set of 2 cells has at least one here. And that means that that makes 2 mines. And so, by that logic, I think none of these are mines. No? Oh, this 2 is a 3. Wait, what? This is at least 1 mine. Oh, I think my logic there was wrong then. Oopsies. There are 2 mines here. Oh yeah, I said 1 mine here and 1 mine here. That does make 2, but we're looking for 3. That's why it doesn't work. I think it might be time to look at the bottom. We know this 3 must be a 2 because it doesn't have 4 cells around it. And this 5 similarly must be a 4. We do know that the 5 must have mines here and here. And the reason why is because if it had any less, you have all 3 of these be mines, which makes 3 in a row. So these are both mines, and by triplet this is not 1. Okay. This 4 cannot be a 5. If it was a 5, then you have 3 mines here. So it must be a 3 as well, implying there's exactly 1 mine here from the 4. This 5 is a 4, which has 2 mines here, and this is actually a 1-2 pattern in Minesweeper, implying this is a mine and this is not. By this 3 then, this is not a mine, and so this is a mine. This 3 sees 2 so far, so it either sees 2 more or it sees no more. Well, if it saw 2 more, that would make a total of 4 around this 2, which fails. So it has to see 0 more, like that. This 4 must now be a 3, definitely. And therefore, because it can't have 3 in a row here, must have its other mine here. This 2 therefore now sees 1 here and 2 here, so this is not a mine. And I think this 2 helps. Because from this 4 we know there's 1 mine here. And from this 2 with 1 mine here and 1 mine here, needs to have more than 2 mines, so its third mine is going to be here. Okay, no 3 in a rows yet. But we do know this can't be a mine because this 5 is a 4. Therefore, these are both mines. This does resolve this place because of this diagonal 3 in a row. So this can't be a mine, this is. Therefore, this can't be a mine. Okay, we don't know about this cell. But yes, okay. Because of 3 in a row, triplet, this can't be a mine. And this 3 therefore can't be a 4, and therefore means this is not a mine. This 4 is definitely a 3, so these are both mines. And by triplet, this is not a mine. This 4 therefore cannot be a 5, so this is not a mine. And this 2 must be a 3, so that is a mine. This 1 is a 2 and is complete. This 6 is a 5, and we know that it can't be 3 mines here. So there has to be a mine here. So by triplet, this can't be a mine, this can't be a mine, and by this 6, which is a 5, these are both non-mines. By triplet, this is not a mine. By triplet, this is also not a mine. I think these 2 means this is not a mine. Right, okay. This 5 must be a 4, because if it was 6, you'd have 3 in a row here. And I believe this 2 is definitely a 3, because it already sees 2 mines around it. But, okay. This 4 must be a 3 though, implying there's 1 mine here. This 5 must be a 4, because it can't be a 5. And therefore, it can't be a 6, I mean. And therefore, because there's 1 mine here, the other mine has to be here. Therefore, by triplet, this is not a mine and this is not a mine. I guess we're using this right now then. Are we looking at remaining mine count? Because there's 1 here as well. 1, 2, 3, 4, 5, 6, 7, 8. 8 cells remaining. Yeah, 8 cells. 8 possible mines. There are, like, you can put a maximum of 8 mines in the remaining cells. Like, you could have a mine here, here, here. I don't know, here, 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 and here. I think that will be fine. Yeah. So what are we looking at then? Alright, I think I get it. This can't be a mine, because if it was a mine, then we know this is not a mine. We would know that this is not a mine as well because of this triplet. Therefore, this 5 being a 4 must have a mine here and here, but this breaks the 2 because we know there's only 1 mine here. So that means that this can't be a mine. So this is this 4 sees 3, so this is not a mine. And this 5 sees 4, so there's one mine here, and therefore no mines here. The one here can only see 2. 1, 2, 1, 2, 3, 4. Yep. And okay, we're gonna cancel this out. We know that there are 6 remaining mines. There's 1, 2, 3, 4 plus 2 from this implies that every other cell must be a mine. So this is a mine, this is a mine, this is a mine, and this is a mine. Therefore, this cannot be a mine, and for the one to remain, these are both mines. There we go. 7 minutes. 7:41. That was cool. That was quite cool. Okay, let's keep going. Outside and wall. Outside means all your mines must connect to the outside, and all the non-mines are together. Wall means that the digits tell you the length of each wall around it. So this one has 3 separate groups of 1 mine. Yes. So let's look at outside first. I don't know how this helps already. But alright, let's see. If this was a mine, right? Because of 1, 1, 1, these can't be mines. Then because of the outside pattern, which is this doesn't work. You know that this has to escape out to the edge, this has to escape out to the edge, and therefore this and this are not together. So that means that this can't be a mine and this can't be a mine. So the 1, 1, 1 is only complete like so, which appears to be fine though. What if I had something like this? Well then, I mean, it's a lot easier to fulfill this 1, 1, 1. You could put something here, or you could, you know, put something here. But the idea is, hold on. What if there were only 1 mine here? I mean, it could always be just... Yeah, okay, let's think about it. If there was only 1 mine here, then there are 2 mines here. But the only way to put 2 mines in there is to do it like this, right? In which case, your 1 mine has to be here or here. Now, wherever your mine is, the other side is not a mine. And the 2 can only... Oh, I mean, you have this option as well. Right, I was gonna say that, you know, this happens, which then forms a deadly pattern. But to be fine, that's fine. Okay. What if this was a mine then? Well, if that was a mine, it must be part of the 2, correct? Yes. And the reason why is because if it was just part of the 1, then wherever you put your 2, you'd have a deadly pattern. So it has to be part of a 2 if it were here. Now, because it's symmetrical, I'm gonna just assume the mine was here. Does that. And this doesn't work because this 2 implies that because of the outside pattern, this can't be a mine. And the only way to fulfill the 1, 1, 1 now is to have a mine here, here, and here, which then forms several deadly patterns. So all in all, that means I don't think this can be a mine. Yeah, alright. Now this 1, 2, and 1, 2 mean that these are both non-mines? Okay. I think this 1 means that this can't be a mine. If it were a mine, then you would have these both be empty. And to avoid deadly pattern, these are both empty as well, putting your other mine here. But now this 1, 1, 1 doesn't have enough space to put 3 single mines. So this can't be a mine. 1, 1, 2. Okay, it looks a bit similar, but I don't know if it is. Well, okay, I'm gonna think about something. Alright, I get it. I don't think this can be a mine. Do I try and imagine if it was? If it was a mine, then these are both non-mines, so the only way to fulfill this 111 is like this. This 1-1 means this happens. Yep, and now this 112 is broken because there's not enough place to put another 1 and another 2. So that I think means this can't be a mine. And the 1, finally, helpful because this 111 implies that there must be at least one mine here, which would then complete this 111. This singular one. What the heck am I saying? Well, what that means is that these can't be mines, and I think these are both mines. Yeah. This 1-1 means this is not a mine. This 2-2 means that this must extend out, and then this is not a mine. This 2 means that's a non-mine. That is a mine, and that isn't. This 3 means that's a mine, that isn't. This 2-2 has a length of 2 here, which must occupy this at least. We know there's one mine here, therefore there's one mine here. But we also do know from this 1-1 that because it already sees one mine, there's exactly one mine here. That will complete this one, so these are all non-mines. Oh, 4, implying that has to be a mine, I think. This one is then complete. I think this 4 can just be completed like that. Yeah, okay. This 1-1 means that's not a mine. And this 2 means these are non-mines. Therefore, this must be a mine. This 3 implies that's a mine, and that isn't. This 1-1-2 over here. Well, you either have... okay, this cannot be a mine. If it was, then your third set would be here, which makes 2 outside patterns. So it can't be like this, and hence... Well, I mean, it can't be a mine here and a mine here either, because then you have an outside pattern. So therefore, it must be this. There you go. 1-3 sees 2 here, which must extend to 3. Is it an outside thing now? Could be. Yes, because this can't be a mine. If it was, then this would block it off, which doesn't work. So that can't be a mine, that is a mine. By the outside pattern, we do know this must extend out. And therefore this 1-2 will be complete, so that's a mine. This must be a mine for 1-1-1, which by outside must extend out. No clues left, but we do have 5 remaining mines. We can see that if this was a mine, then these 2 have to be mines to ensure no non-mines are isolated. And same for these 3, but look at that, we have used 6 mines total and there's only 5 remaining mines. So in all, that means this can't be a mine? Yes, and this 1-1 implies they're both empty. This 2 is complete, this 2 is complete, this 3 is also complete. And 5 mines remaining means these are all mines. That's great. Wow, okay. 7 minutes, again. Cool. We'll take it. This was fun. Like at the very beginning. Just trying to break into the puzzle was already challenging. But okay, dual and negation. So dual implies that, dual means that your mines must form 2x1s, dominoes, that they cannot touch each other. Negation means that the numbers tell you the difference between the light mines and dark mines. In this case, you can consider light mines to be positive mine values, and then negative mines to be negative, darker mines to be negative mine value. What am I saying? And then the number gives you the absolute value of the difference. So, let's begin. This 1 over here, well, dual, firstly. Therefore, if this was a mine, it must extend out to here. And because of dual, these are both empty, and so is this actually, but the 1 is now broken, because it sees 0. 0 difference. So, that cannot be a mine. Therefore, one of these are mines. To ensure 0 works, then this must be a mine, and that must be cancelled out by this. So that's our first dual, which does that. This 0 is complete, so that's not a mine. This 1 sees 1 already, so that's not a mine. Well, we know from this 1 that because it sees 1 already, this must add to a 0. This 1 means this must add to a 1. I'm gonna say blue is 0, and then we'll do yellow to be 1. Sure, you can see it. Therefore, for this 0 to work, this must be a mine to cancel out whatever is here. And because it's a light mine, it must be cancelled out by a dark mine. That's another dual. Because we know this is a 0, which I should have marked in blue, then we know this can't be a mine either. Well, we know there's one mine here, which means that there is exactly one here of some sort. This 2, therefore, well, we don't know, but we do know that if this was a dark mine, this is not a mine, and therefore this 2 seeing 0 would be unable to be fulfilled. So that means that the light mine must be the one. And for the 2 to work, this cannot be a mine. This mine must extend out to form its dual. And this 0 must have its second light mine cancelled by a dark mine. So that's not a mine. From this, we know that it either goes out to here or here. And either way, this is not a mine. Also not helpful. Alright, I think it's probably this 1 then. Yes, because this 1 can only be fulfilled in a few ways. It could either, because it's C0 so far, right? It could either mean that this box over here, the possible values it could contain is a -1, if there's one mine here. But we know that's not possible, because these can therefore be non-mines, and that isolates this one. So it can't be a -1. Could it be a 0? Well, yes it could. Could it be a +1? Could also be a +1, and there are a few ways for it to happen actually. You can have a mine here, that works. You can have a mine here, that works. Because then they could both extend outwards. How about 0? How would 0 work? Well, if it was 0, it definitely implies that, well, there could be no mines. Could also be a light and a dark, which must be like this. I was wondering, can this be a mine? The answer I think is yes, although I'm not entirely sure. No, I think it's a 0. Right, this 0 cannot have a mine here, because if it did have a mine here, then for the 0 to cancel out, it needs 2 light mines, which then makes 3. It does not work, so this can't be a mine. 0. Okay, well, we know from this 0 seeing a dark mine that it needs to see a value of +1 up here. This 0 must therefore see a -1 down here. We therefore know that if this was a mine, then for the -1 to be happening, these are both mines, which then breaks again. So again, this cannot work. There we go. Well, the 1 sees this happening already. Therefore, for this to make up a 1, you either have a 0 here, or a +2 here. But we know that +2 doesn't work, because we know that in total there must be a +1 only. Although a +2 here does work if, say, you have a mine here and a mine here, and then extending out to here. And you could have like the dark mine be here or something. Yeah, in fact, this cannot be a 0, because if it was a 0, then how do you even make a +1 in these 4 cells? So it must be then a +2. Like that. Yeah, okay. We know that therefore one of these are mines. Correct? Now, whichever is a mine, in this set over here, this must be a mine in the opposite corner. I think same works here and here. So in all cases, your dual is going to be a horizontal set, meaning that these are not mines. Yeah, okay. Again, you know one of these are mines. In that case, that forms a 0 in this region, implying that if this was a mine, then you have to have a dark mine cancel it out. And then these have to be both empty, because you can't cancel those out anymore, and that isolates this mine. So I'm pretty sure what that means is that this cannot be a mine, which it isn't. This dual must then come out. That happens. This one sees a 1 already, so this can't be a mine. And this one means this is a mine, which must come out. This one sees 0 so far, so one of these are mines. Oh, no, it sees this as well. Yeah, okay, so this sees what? A 0 so far? A positive 1 so far. So it needs to see a 0 here. That means in total there is a positive 1 value here, meaning that there must be a negative 1 value here. And by the same logic we accounted before, I don't think this can be a mine. Yes. Ooh, this looks similar. Yes, because we know that there is a negative 1 here. So to preserve a 1, this must also be a mine. In which case, this 1 means that this has to be a mine. Then by dual, this cannot be a mine and this must be a mine. And then this is not a mine, so this is a mine. Therefore, this is not a mine. Okay. 4 mines remaining. We know one of these are mines to complete the 1. One of these are mines to complete the 1. We don't know if it's positive or negative, but whichever is the mine, it must extend out vertically. You either have this or you have this. In either case, it would take 2 mines in these cells. This 0 sees a 0 so far. So to see another... Well, it can see 2 more if it wanted to, if it can. It can if it wanted to. But I don't think this can be a mine, can it? Yes, because if this was a mine, then we know that the 1 cannot do this and therefore must do this. In that case, this one must extend out to here, and therefore these are non-mines, and the 0 is now broken. So that means that this cannot be a mine, and that's a 1. Well, we know because out of these 4 cells is either here or here, then that makes this set essentially equal to a 1 of some sort. Therefore, say this was empty, I'm pretty sure this must be a 0. Yes, because if it were a 1 of some sort, assume it were a 1, it must be a positive 1 and be cancelled out by a negative 1 here. In which case, for a 1 to happen, you know, you would... I mean, it really wouldn't work, right? Well, no, then this has to be a mine. And that fails. And the reason for that is because you already have 2 mines here. You have 2 mines here and 1 mine here. That makes up 5 mines at least. And you only have 4 remaining. So this 1 cannot see a 1 here. So must see a 0 here. Implying that firstly, this must also be a 0. This must also be a 0. And because it's a 0, there must be at least 1 mine here. Now again, we know that there is 2 mines here already. And then from this 1, we know that there must be another 2 mines here to form another dual. That uses 4 mines, and therefore this 0 here cannot have any mines in it. There we go, nice. Right. We now notice that if this happened, then the 0 must have a light mine cancel it out, which breaks dual. So this has to happen. Then this one has to be cancelled out by a dark mine, which does this, and which must extend out to here. So there we go. Whew, that was cool. A lot longer than previously, but still decently fast. Jeez, I'm sorry that was really loud. Okay, I think we can do 1 more, and then we have 3 more to finish off the entire thing. Or maybe like I'll just end it here, go and rest a bit, and then like the 4 more. Oh, there's a Q and M. We actually haven't done a Q and M combo yet. Very surprisingly, because that was the very first combo we were introduced to. Q and M. Although like Snake is actually pretty fun, so I might want to try Snake. Okay, let's do Snake. So what are the rules? Snake means that your mines must form a snake. Trivially. They can't branch, they can't touch each other. The cross over here means that the numbers talk about the 8 cells in the plus shape around it. So let's begin. We start with a 1 here and a cross and snake value, because if this were a mine, then from the 1 this would be empty, this allowing the snake to come out, which means that this can't be a mine in general. 0 is helpful. 0 again helpful. I think this 2 means that these are both mines now. Therefore this is not a mine. This is also not a mine. 4. Alright, well, we already have 1 dead end. So 1, 2, 3, 4, 5. Alright. Yeah, this 4 sees 5, right? I want to say something very interesting about how dead ends work here. Because we always know that this 4 has some dead end around it, I think. If this was a mine, then there's clearly a dead end as it enters here. But assuming this was not a mine, then you would have this. Right? Because we now know that this thing cannot branch, this is not a mine, you therefore have this 2 block, which is also a dead end in Snake. Because you can't exit it, otherwise you touch yourself. Which means that there is always a second dead end here. And because there's already 1 here, we know there cannot be any more dead ends anywhere else in the puzzle. And therefore any mines in here, which would constitute a dead end, would break the puzzle, and therefore there are no mines here. Cool. This 2 therefore means this happens. And because no dead ends, this cannot be empty, otherwise you'd have this dead end here. So it must go like this. This one must continue out, because it's not a dead end. Like that. And so you have this little like thing coming around like here or something. Your snake could look a bit like that. In fact, because of this, it must come out to make a mine here. Yes, okay. Next. There are a few, like, maybe a few possible... Yeah, the idea is that... Yeah, this can't be a non-mine. If it was a non-mine, then because the 4 has to be completed like this, your snake must exit out to here, forming this, right? But to get to the other dead end, you'd have to loop around back in this direction in some way, which would then make you touch it will make the snake touch itself. So yes, this cannot be a non-mine. Therefore this must be a non-mine because it can't branch out. This cannot be a non-mine now because a mine here would form a dead end. So this must be a mine. Therefore you either have a mine here or a mine here. I don't think it's very conclusive. Yeah, I don't think it's conclusive. I don't think it's conclusive. Alright, so how the heck do we even do any snake? How do we do any snake shenanigans here? I mean, like, the path could go as crazy as to do something like this. I think that's a valid path. It does use 15 cells or something. Four, 6, 8, 10, 12. Whoa, what the? Wait, really? No way, no way. No way this is just it. Hold on. What is the shortest path you could make here? Because this must go here in some way, then the shortest path you can make is probably something that looks a bit like this. The snake must then continue up and take the shortest path, which is probably just a straight line over here. And then it could come down here. Okay, so this is the shortest path, which takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, it could always go down here to take 11. But in that case, it could always extend itself, you know, to do something like this, or this, to lengthen its snake, which is fine. That's doable. So I'm just thinking about like what. Let's say this happens then. Then clearly this must happen. But if this happened, oh, now we use parity, right? We use parity, yes, because to get all the way around to this point, we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 mines. And we know because of like how snakes work, to get from point A to point B, if it uses an even number of mines, then any other path ever would also use an even number of mines. But here we have an odd number of mines remaining, which doesn't work. So it must extend itself to an odd number. Therefore, I think this is always a mine. Yeah, okay. I don't know how else we can get any information out of this though. Like, okay, let's say this goes up, right? Then again, the minimum path would now look something like this. Then because it can't touch itself, then the minimum path will look like this. And do that. Is this breaking already? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It barely works out. So it is possible. It is possible. What? Then what? Oh, then I get it. It can't take anything up here. Because if you take anything up here, right, you'd have to take the long way around from one end to the other end. These cells inside can't reach the outside, otherwise you block your path off. And this path, I think 2, 4, 6, 8, 10. This path takes 12. Oh wait, doesn't this work then? Could your snake look like this? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It could, what? Does that mean that maybe your snake can't do something like this? How could your snake go in here then, maybe? Again, taking the shortest path, we realize that the only way to make the snake go in here... Oh, it can't. Because to go in here, if it went in here, it can't be a dead end, correct? So you can't make this a non-mine. So then this has to be a mine. But then because it branches, it can't branch, I mean. That can't be a mine. Which would make this its own dead end. So no mine can actually come in here. Oh, and there's the next clue. Alright. Fine. By cul-de-sac. This can't be a mine, this can't be a mine. This too. Well, this must be a mine because you can't, you know, isolate them. And then this must be a mine. So that this can connect to here. So that's not a mine, that's not a mine. Okay. This too. Well, there must be some number of mines here, right? Does that mean we need to take the shortest path now? Does that mean the absolute shortest path implies this? Because if we did this... Well, I mean... Yes. If we did this, that doesn't work. Because, okay, yeah, I don't think even if uses a 2. If this was a mine, then this can't be a mine, otherwise your snake would be really short. So that means this isn't a mine. But then that really just isolates this set. So it can't extend out and must do this. It cannot then extend out to here because otherwise this would be empty and isolates this end. So that happens. 3. Again, this must extend out to here. This 3 sees 1 so far, so it only sees 2 more. Okay, well, I think we can use the 3 and the 2 together. This 2 either has a mine here or a mine here. Now, if it had a mine here, then this is empty and this is empty. How would this mine go all the way? It would take the long route. Right? Yes. And then that takes 1, 2, 3, 4, 5, 6, 7, 8. That will take 9 mines in total. And because we have 10 mines remaining, one of these has to be mines. I mean, it has to be this one, so the 3 is... Oh, the 3 is not satisfied. Oh, then yeah, then the 3 is never satisfied. So this is not possible then. In this case, the 3 cannot be satisfied with 2 more mines because we don't have 2 more mines. And so this doesn't work. I mean, okay, it's not that it doesn't work. It works if this happened. Right? Yeah, and then it also works if this happened. Well... No, I don't think this is... I don't think this can be a mine. Alright, let's see. If this was a mine, then this can't be a mine. So this has to be a mine to bridge it. Then this happens. Oh, and that's another dead end. Alright, that's fair. So this can't be a mine. Otherwise it'll be a dead end. Another 3. Well, there must be some number of mines coming out here. And then... what? Let's say this was a mine. Then this can't be a mine, right? Because if it was a mine in this case, then this must be a non-mine and this must be a mine. Which then breaks the 3, which sees 4 now. Okay. So what that means is that this can't be a mine. Therefore, this is a mine. And then because of this 3, this happens. Is this possible? I think it is. If your snake went around like this, it's possible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, okay, fine. I think that's possible then. Well, what if this was a mine? We know that I don't think this can be a mine. Because if it was, then these are both empty, which breaks the 2. So that can't be a mine. Because this can't be a dead end, it must extend out in both directions. Oh, alright, and that doesn't work. Because this 3 now already sees 3 mines, so these are both empty, which isolates this set of mines. So this can't be a mine either. 4, this is gonna keep giving me numbers. It's always just one cell at a time. Oh my gosh, okay, well. We know that this must exit through here at some point, which must then exit through here at some point. That puts at least 1 mine here and at least 1 mine here. Wow, okay, then what? If this was a mine, then we know this can't be a mine, so that happens, which makes this a non-mine. Right? Yeah. And this must be a mine for the mine to come out. The 4 is then complete. But this is an okay path. This works, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it works. I think. I don't know about this 3 though. Like the 3 seems very sus. Oh, it doesn't work. Okay. Let me just try and look at this first. If this was a mine, oh my gosh. If this was a mine, then this has to happen. This has to be a mine, which then completes the 4. So this happens. And then the 3 is broken, because it can't make 3 mines. Alright, so let's... I assume that means that this is not possible then. Alright, fine. Jeez. Okay, what now? Let's see. Alright, This tree can only see one more. Ah, and therefore now a lot easier is if this was a mine, then this 3 implies this is a non-mine, which isolates this chain. So this can't be a mine. Jeez. Does that make it any easier? I mean the 4... I don't know about the 4. Oh, although I do know this has to come up to here. That helps, because this 2 means that this can't be a mine now. This one must definitely come out to here. Because we have 5 mines remaining. Well, I mean, there are a few ways to do this. I can do this, I can do this. This. Or just any combination that does that. Like, I think they call it a taxi cab distance. The total number of vertical and horizontal steps you have to take. A taxi cab's distance of 5. It's all 5. So I think it's just down to the numbers. This 3 does mean this is a mine though. Oh. And now I think because this mine exists, you can't just take any of these, right? If you were to take some of these, you would spend way too many mines here. So I don't think any of these are mines. Yes. Which therefore implies this must be a mine and this must be a mine. The 4 now is completable by putting a mine here. That's not a mine then. This 3 is complete, so that's not a mine, that is... Oh, wow, that was fair. The longest one yet. That took very long. Jeez. 17 minutes. It was like at that last section, it was just clue by clue. Oh my god, but look at the snake's path. That's such an awesome path for a snake to take. I have no idea why I'm drawing it, but wow. Yeah. So anyway, cool. Hope you enjoyed it. We have only 3 more, which we'll complete next episode, but yeah, until then, see ya.